right, welcome back. And what we're going to be talking about is trig substitution. And in this one, in our final tutorial of how to use trig substitution in order to solve various integration problems. In this one, what we have is the integral of dx over x squared over the square root of x squared plus 1. Once again, trig substitution is a last resort. I cannot stress this enough, people. This is the last resort. You do not want to use trig substitution every time. However, if you have to use trig substitution, how do you identify it? Well, one of the key things is, for one, use substitution you can't use. Partial fractions you can't use, and parts you can't use as well. And what you notice is there's also a square root, all right? Or you can create a square root in the denominator or numerator where you have possibly the difference of squares, and this is the, not the difference, but sum of squares, binomials where you have x squared plus 1. My other two tutorials we had is x squared minus 1 or 1 minus x squared, and so on and so forth. Well, in this case, when you see two squares, binomial with two squares in the square root, this is where we're going to use trig substitution. And when we're doing this, we're going to identify, all right, our variable, which is our u, and our a. In this case, we're going to be using tangent. Tangent. All right, so this is trig substitution using tangent. So when you see x squared plus 1, that's tangent. X squared plus 1 is tangent. Or any square plus another perfect square, that's tangent. Now, we're going to set up our triangle. All right, and you're going to see that I outlined this and probably did it a few other times. All right, that's a horrible outline. I'm going to just get rid of that. All right, but in our outline and in our triangle, we're going to take the tangent of this angle. Tangent, if you recall, is equal to opposite, that's TOA, opposite over adjacent. All right, adjacent. And that's the ratio we have right there, opposite over adjacent. So in our opposite is our numerator, and like the previous ones, that is where our variable is going to be, right? Our u. Now in this case, our u is actually x, because that u is being squared, and that's going to be our x right there. The a value is right here, okay? And a is going to equal 1, all right? Because that's what's being squared, 1 is being squared, and that a is going to equal 1. Once we have that, we can use Pythagorean theorem to figure out this side, which is actually going to be that portion right there. So you only use the square roots. If you're wondering what the x squared we're doing right there, don't worry about it. Look at the square root. And we're going to have the x squared, all right, plus 1, and that's going to be our solution. All right, now, once we have this set up, we're now going to set up our ratio. Okay, so we're going to set up our ratio now. So we're going to take tangent of theta, and that's going to equal opposite x over 1. All right, and what we have right here is going to be just tangent of theta equals x. All right, tangent of theta equals x. Now with that, we can start using substitution, because you notice for all the x values, we can start plugging in tangent of theta. So we can write the integral. We have dx right here, all right, dx, and we'll have tangent squared of theta. I'm plugging in for x, and then we'll have the square root of tangent squared of theta plus 1. Okay, okay. All right, from here, notice that we still have this dx. Well, I want to get rid of that, so we're going to take the derivative of this with respect to theta. When we do this, what we have is we're going to do that so we can get actually dx by itself, create a differential. We have the tangent of theta, which is going to give us secant squared, all right, of theta, equals the derivative of x with respect to theta is going to be dx d theta. And we can multiply both sides by d theta. And so we get dx by itself. So we have secant squared of theta d theta equals dx. And there we have it. So we're going to use tangent. And now we can use this, and we're going to finish our substitution. So I'm going to plug that in there. I'm going to have secant squared of theta d theta. And I'm going to plug that in for dx. That right there. So you can notice that. All over, we're going to have the tangent square root of theta. And then right here, we have another identity, another substitution we can do, because this will always turn into some sort of identity. In this case, we're going to use tangent squared theta plus 1 equals secant squared, one of the basic trig identities. And we're going to solve for this by taking solve for secant. We realize that's going to equal secant. So we're going to use a little substitution. It's Cajun for substitution. All right, and we have that. All right. Now from here, I'm going to start changing colors because now we're going to simplify this a little farther. This and this can cancel out. And now I'm going to turn this into green. All right, I'm going to use purple. All right, and we're going to have the integral of secant. All right, secant of theta. And since it's a reciprocal, I'm going to go cotangent squared. That's a reciprocal tangent, right? All right, cotangent squared of theta d theta. All right, now from here, we're going to have to do a little simplification. This doesn't work out. Now, usually when we do this, we're going to simplify this and create a simpler integral. So let's, what I'm going to do is I'm going to switch this around a little bit. And I'm going to create secant into 1 over cosine. I'm going to see if good things happen. Usually the good things happen when you switch this up. So we're going to have sine squared. Oh, yeah, cosine. Oops, that's all right. Let's erase that. Sorry, not sine. Cotangent is cosine. All right, cosine squared of theta over sine squared of theta. All right. From here, we can also realize that this can also cancel out. So we're going to cancel that one out. That turns to 1. And so now what we have is cosine over sine. All right, cosine of theta over sine of theta. And I'm doing this for a reason. Over 1 over sine theta. I broke up the little sine squared theta right there, and we can write it like that. The reason why we're doing that is because if you realize, hopefully, cosine over sine is cotangent of theta. And right here, what we have then is going to be cosecant of theta d theta. And yes, this is a basic trig, or basic trig integral. And what is that going to equal? Well, it's going to equal negative cosecant of theta, because the derivative of negative cosecant theta is cotangent theta cosecant theta, and that's what we have right there. Oops, why did I have this? That's not going to be right. I finished my integral, so we have negative cosecant theta plus c. Cool. So we have negative cosecant theta plus c, and now this is just like all the other ones. Once we simplify this into one simple integral, we're now going to go back to our triangle. We're looking at cosecant. Cosecant is reciprocal of sine, all right? And what that's going to be is hypotenuse over opposite. So we're going to take the square root of x squared plus 1 and divide that by x. So we're going to write that as negative square root of x squared plus 1. Divide that all by x, and then add the c. And there we have our final answer. There you go. Easy peasy. All right. Lemon squeezy. All right. So with that, using trig substitution, we got tangent. We can use solving a problem like this, looking for the square root, set up our triangle, set up your tangent ratio by using all those different parts, taking the derivative, plugging it all in, create that simple little integral that you can solve. All these, usually if you can't use a calculator, are like this. So hopefully this helps you out. And I have the other two problems dealing with secant and also sine. So if you have any other questions, you can check out those two as well. So good luck and God bless on the rest of your problems.